In this video, I'll be going over the Unit 7 geometry test, which includes inscribed angles, central angles, shapes inscribed inside of circles, circles inscribed inside of shapes, by shapes I mean polygons. And we also have a vocab section, and there's one section about the area of a parallelogram. So as we work our way through, we'll start with this question 1. A circle is circumscribed about triangle GMC. So basically GMC is inscribed inside of the circle. Given that the measure of arc MC is 66 degrees and the measure of angle GCM equals 73 degrees, we need to draw this figure, label all the internal angles of triangle GMC with their measures, and label the arc measures of the 3 minor arcs on the circle that are created between adjacent vertices of the triangle. All right, so let's take this one point at a time. So first, if we're drawing it, we've got a triangle and it is inscribed inside of a circle. Right, we can say the circle is circumscribed about this triangle. So like something like that. Arc MC is 66 degrees. So you can see I already drew it not perfectly, because that should 66 degrees, it's 66 out of 360, so it should be a little over a sixth of the triangle. It seems to be more than that. And angle GCM is 73 degrees. So this is the one that has C in the middle, 73. So that actually looks fairly accurate. It's pretty much the issue is G should be smaller because it should be half of 66. So if I'm going to redraw this, I might actually just switch G and M. G up here, because it's supposed to be the small angle, M down here. C is still 73 degrees, and arc MC is right here, has a measure of 66 degrees. All right, so those are the two givens. What we need to use for this problem is the fact that all of the angles in a triangle will add up to 180. All of the arcs, if you have, none of them are overlapping and they take up the entire circumference, they should add up to 360 degrees. And we have the fact that inscribed angles, so in this case, like angle G is an inscribed angle, goes all the way to the edge, will be half of the measure of the arc that it intersects. So if this arc is 66, the inscribed angle should be 33. A central angle would be the same angle, so if you did it to the actual center point, like this angle would be 66, but we don't need that for this triangle. It's only going to be inscribed angles. So we have 73, 33, and we know that angle M will add up with those two to give us 180 degrees. So we can just do 73 plus 33 gives us 106. 106 plus the measure of angle M equals 180. Subtract 106 from both sides. You get that the measure of angle M equals 180 minus 106, which is 74 degrees. Okay. So it's almost an isosceles triangle, but you see angle M is a little bit bigger, which means side GC will be a little bit bigger. Again, not drawn perfectly to scale here. So now if we need to find the other arcs, we'll just double the inscribed angle that's intersecting with them. Right, so this one is 74 degrees. If we double 74, that gives you 148 degrees. Now for the last one, you could do 360 minus those other two, but I'll just do 73 doubled, which would be 146 degrees for this measure of arc GM. And I'm just going to write that. So we've got the measure of angle M equals 74 degrees. We calculated the measure of angle G equals 33 degrees. That was doing half of 66. They gave us angle GCM is 73 degrees. You could also just call that angle C. And now for the arcs, as we said, the measure of arc GM equals 146 degrees. And the measure of arc GC, what's called CG, is 148 degrees. Now, what I recommend is when you're checking this, and you could even rewrite this one if you'd like, and rewrite this one. But when you're checking this, make sure that all of these add up to 360. So that's why I didn't use 360 to do it, because now I could go, all right, well, 146 plus 148 plus 66, that gives me 360. So that checks out. So label all of the internal angles. We've got all of them labeled in here, 1, 2, 3. And we also have to label the arc measures of the 3 minor arcs, so they're less than 180. All of them are less than 180 of the circle that are created between adjacent vertices. So between G and M, between M and C, between C and G. We have all 3 of those. All right, on to the next one. So we have this pentagon that spells out Shrek, but they're calling it Kurs, is inscribed in a circle as shown below. Side SH is congruent to side SK is congruent to side RE. So those are all chords. If they're all equal, that means that the arc that they intersect, the arc they capture, is going to also have the same measure because they're the same length chord on the same circle. We'll keep that in mind. They also give us that the measure of angle S is 74 degrees. And the measure of angle K is 122 degrees. I will start by trying to find this arc, and once you have that arc, you can also get this arc, because we know they're the same if they have the same chord. But to do that, I'm going to draw this triangle up here. So triangle HSK, it is not going to have 122 degrees in it, right? It's cutting that into a fragment. But because we have these two sides are the same, so SK and SH are congruent, that means that it's an isosceles triangle. The opposite angles will also be congruent. Angle SHK is the same as angle SKH. Now that helps us because we know the angles in a triangle add up to 180. So if we have 74 degrees plus 2 times, let's call this x, 2 times x, that will give us 180 degrees. Subtract 74 from both sides, and we get that 2x is equal to 106 degrees, which means that x is half of that, 53 degrees. So we've got 53 degrees here and 53 degrees here. Now that also will help us find HKE, so this angle right there, because we know 53 plus, we could call this, I don't know, y. 53 plus y equals 122 degrees. That entire angle K is 122 degrees. So subtract 53 for both sides, and that will give us 69 degrees. All right, so we've got 69 degrees down here for angle HKE. If we want to find the measure of arc SK here, we know it's going to be double the inscribed angle that intersects that, and that's down here. So double 53 degrees gives us 106 degrees. We could use the same logic to find this arc up here, arc SH. However, you could also use the fact that they have the same chord intersecting them. So the same chord intersects those two arcs, which means if this is 106 degrees, this is also 106 degrees. Right? That works because the same length chord on the same circle will always intersect the same arc. So the same thing is true of this arc down here, arc RE or ER will also be 106 degrees because again, it has the same chord intersecting it. So we're most of the way done. Now we can fill these in. What is the angle measure of the minor arc HS? So HS we said is 106 degrees. What is the angle measure of minor arc RE? So we just said that that is also 106 degrees. I don't think I asked for arc SK, but you can label it in there, get it correct. What is the angle measure of minor arc HR and KE? So we need to find out these two. So we know that they're all going to add up to 360, but first we need to find one of these, and then we can use that 360 to find the missing one. We know that this angle here is 69 degrees, and it intersects not just one of these arcs, not just HR, but H all the way over to E. So HRE, that minor arc right there. Now, if you want to find the angle measure of HRE, again, you double the inscribed angle that intersects it. So double 69, which would give us 138 degrees for this entire measure of arc HRE. And the measure of HRE is also equal to the measure of HR plus the measure of RE. Right? That's how you form that arc, is you add those two smaller arcs together. So we could say that the measure of arc HR plus the measure of arc RE would be equal to 138, right? Because it's equal to HRE, which is 138. Now from there, we know that RE, the measure of arc RE is 106 degrees, so we can plug that in. And now we know that the measure of arc HR plus 106 degrees equals 138 degrees. So basically we're saying 106 plus something makes 138. You have to figure out what that something is. In this case, if you subtract 106 from both sides, or just think what plus 106 makes 38, it's going to be 32 degrees. So we've got 32 degrees up here. This part is 32 degrees. Again, the 138 is just talking about the entire thing. And now that we've got that's 32 degrees, we can label it on our answer. And we know that all of these arcs, so 106 plus 106 plus 32 plus 106, will all add up with this last arc, arc KE, to make 360. So if we add them all together, we get 106 times 3 is 318. 318 degrees plus 32 degrees plus the measure of KE gives us 350 degrees plus the measure of KE equals 360 degrees. So the measure of KE must be 360 minus 350, which is 10 degrees. All right, so we've got 10 degrees right there. Now I've taken over some of my space here, so I'll move this up. And it says, is arc KSH a major or minor arc, and how do you know? KSH goes from K to S to H. So it's 106 plus 106. So that entire arc has a measure of 212 degrees. Now the reason that I'm finding the measure is a minor arc is an arc that's less than half the circle, or less than half the circumference. So it's going to be less than 180 degrees. If your arc has a measure that's greater than 180 degrees, then you know it's actually a major arc. So in this case, it is a major arc. And they say, how do you know? Because the measure of its arc KSH is greater than 180 degrees, right? It was 212 degrees. So that's all you've got to do for that. And now if we move on here, we've got a little square is inscribed in a circle that is inscribed in a bigger square. The perimeter of the bigger square is 48. So for a square, to find the perimeter, you're just doing 4 times the side because you're adding up the 4 sides. They're all the same if it's a square. So 4 times the side equals 48 centimeters. If you want to find what one side is, you just divide by 4 and you get 12 centimeters, right? You can even check that. 12 plus 12 plus 12 plus 12 would give you 48. Right, so all of our sides are 12. What is the circumference of the circle? So to find the circumference, we know we could either do our formula circumference equals pi times diameter, or you could do circumference equals 2 times pi times the radius, right? 2 times the radius is the same as the diameter. In this case, if we look, because the circle is inscribed in the square, the diameter will be the same as the side length of the square. It's touching here, it's touching here, so the longest distance across is the side length. So if our diameter equals 12 centimeters, then our circumference will be pi times 12 centimeters, which you could write that as 12 pi centimeters. Or if you'd like, you could also type that into a calculator. So I take my calculator here, I would write 12 times pi, and it gives me 37.699. This is about equal to 37.6991118, something like that. And on this, we're rounding to the nearest hundredth. So a lot of students here, because this rounds up, they wrote just this as their answer. But technically, you should still keep it to the hundredths place, even if it's a 0, because that's still a rounded value, right? It's not exactly 37.7. So you could say 37.70, again, keep your units, it's centimeters. Now we don't do centimeters squared because the circumference is just a distance around. So either of those answers would be acceptable. This one would be the exact answer. This is the rounded answer. What is the perimeter of the little inner square? So we need to find the side lengths of this little square. In this case, those will not be 12. But what 12 will be in this square, usually if you have a shape inscribed in another one, especially if one of them is a circle, try to find a way to relate the two. So in this case, the circle's diameter, you can also redraw it right there, and that's the same as the diagonal of the square. So a diagonal of a square will always be equal to the side times the square root of 2. If you don't feel confident in that, just remember that you're cutting the angles in half. All the angles in a square are 90. So we've got a 45, 45, 90. Right? In this case, the hypotenuse is 12. The ratio of the sides of a 45, 45, 90 is side root 2 for the hypotenuse. So in this case, side root 2 is equal to 12. So if we want to find the side, you just divide both sides by the square root of 2. So it'd be 12 over the square root of 2. You can simplify that by multiplying it by root 2 over root 2, which gives you 12 root 2 over 2. And then again, you could divide that. 12 divided by 2 is 6 root 2. Okay, so the side length is 6 root 2 for this little square. And that's 6 root 2 centimeters. Now I'm not going to round that yet, but this is what's the perimeter of the little inner square? Well, the perimeter is just 4 of the sides. So if the side equals 6 root 2, then the perimeter equals 4 times the side. So that's 4 times 6 root 2, which will give me 24 times the square root of 2 centimeters. And again, if you would like to give your answer as a rounded value, because 24 root 2 is technically the more exact, it is the more exact answer. But you could also type 24 times the square root of 2 to your calculator. Gives me 33.9411255. And I always round way beyond what I need. Because again, we're going to the hundredths place, but I'll round it beyond what I need so then I can round it when I'm giving my answer. So in this case, that would be 33.94. Again, don't forget your units, centimeters. What is the area of the little square divided by the area of the big square? In this case, you could find the areas of both. So you could do 6 root 2 squared, right? The area of the square is the side squared, divided by 12 squared. Now make sure, a lot of people mess this up. It should be little square divided by the big square. So it should be less than 1, right? Because you've got the smaller one over the big one, right? It's a small to big ratio. That will give us 6 squared is 36, square root of 2 squared is 2. So 36 times 2 over, you could do 144, or I'm just going to write it as 12 times 12, because I know I can take out a 12 from 36. So that would leave me with 3. So now we've got 6 over 12, which is equal to 1/2. All right, so you could leave it as 1/2. Some people wrote 0.5, that's fine. Now, for the units, there actually won't be any units, even though it's area, so you'd think it's centimeters squared. it's area divided by area. So we're getting centimeter squared divided by centimeter squared, which cancel out. So it's just a ratio, you just leave it as 1/2, right? So if you've got 1/2, 24 root 2, or again, you could round that value, and 12 pi centimeters. Next, onto the vocab section. Got a word bank down here and a picture bank. Let's see, it says a straight line segment connecting 2 points on a circle or a curve. So a straight line segment connecting 2 points. Well, that would just be a chord, right? So like you could even see PQ right there is a chord. So that's figure F, and it is a chord. Now it was not mean on here, so all of the letters are used once, all the words are used once. An angle that forms when 2 radii meet at the center of a circle. So the angle formed when 2 radii, well, we've got a radius and a radius right there, so it looks like B. And now looking at that picture, this is the central angle, right? So that would be central angle. And these are a little bit, they're worded a kind of a weird way. We did that on purpose, you'd have to think about it. And this one, an angle formed inside a circle when 2 chords intersect on the circle. Okay, so it's an angle inside the circle. Well, here's an angle inside the circle, and this is a chord, and this is a chord, right? They're intersecting. So that's A, and A looks like an inscribed angle. It's an angle that's fit all the way to the edge of a circle like that. We've got inscribed angles and triangle. We've already got the first 3 done, and now an angle formed between adjacent sides of a polygon. So it's two sides between adjacent sides. So it looks like it's talking about inside of it. So that should be C, and that would be an interior angle. And you could argue, well, the exterior angle is not, well, if you extend this side out, then it's between these two, this side and this side extended, but they didn't specify that, so let's make sure that the other one does that better. An angle outside of a polygon, so we know it's outside, well, that would be the exterior, formed between a side and an extension of the adjacent side. So this is exterior angle. So even if you were a little bit ambiguous based on this first one, this next one is clearly the exterior. And a line from the center of a regular polygon at right angles to any of its sides. Okay, it's kind of a weird way of wording it. We know it's going to be E, assuming we got the other ones right, but this is called an apothem. And it will occur when you've got the circle inscribed inside of a polygon, right? Then the radius will be the apothem if it's a regular polygon. All right, so that's all you've got for those ones. Make sure that you've labeled them all correctly. Here we've got what's the area of the parallelogram below. So we know for a parallelogram, you could break it up into triangles and rectangles. In this case, it might be a square. So that'd be fine. Like you find the area of this, find the area of this, find the area of the rectangle in the middle. That will get you the correct answer. And if you don't feel confident in the formula, that's fine. If you know the formula though, the area of a parallelogram is going to be equal to the base times the height. Now, when we say height, it doesn't mean, right, like this is the height and this is the base. Height has to be an altitude. It has to be perpendicular to the base you're doing. So in this case, what I would do is this base down here, which is the same as AT for a parallelogram, right, opposite sides of the same length. And you can just count the length of it by going 1, 2, 3, 4, 5, 6, count the squares. Or you could go, all right, it goes from -4 to 2. So the difference between -4 and 2 is 6. And then the height will be perpendicular to that. So going like this way. And again, you can count the squares, 1, 2, 3, 4. Or you could go, okay, well, it's going from -2 up to 2. That's a distance of 4. All right, so our base is 6. Our height is 4. The area will be those two multiplied, so that would be 24. And now there are no units. Some of my students will write unit squared or u squared. I would probably accept it just as 24 as well, but that's all you've got to do for that one. Don't waste too much time. This one was mostly thrown in as a freebie. And next we've got a regular octagon is inscribed in a circle with radius 4 centimeters. What is the perimeter of the octagon? What is the area? And what is the area that is inside of the circle but outside of the octagon? So basically we're trying to find like these areas will be the last part. All right. Well, in this case, it's a regular octagon. So all the sides are the same, all the angles are the same. We can divide it up into triangles. It would be like 8 slices of a octagonal pie. If I had drawn this perfectly, it should all pass through the middle there. So all of these triangles would be congruent because it's regular. So all of the sides are the same, all the angles in here are the same. We want to find this angle up at the middle. We know that that entire circle that I just drew is 360 degrees. We're cutting it into 8 slices. An octagon has 8 sides, and each side has its own triangle. And we get 360 divided by 8 gives us 45 degrees. So each of these angles up top is 45 degrees. Right? If we want to find the perimeter, we need to find the base here. So we need to find one base because the base of these triangles is the side of the octagon. And to find the perimeter, you just add up the sides of the octagon. In this case, all the sides are the same, so it's going to be 8 times one side. If we want to find that base, what we can do is make a right triangle. So we could use any of these triangles because they're all congruent. So make a right triangle by dropping it down. We know that these little pink triangles I made are isosceles. This angle is the same, this angle is the same, because it's regular, right? That will be the case. Which means when you drop down in altitude, it will cut the angle in half, it will cut the opposite side in half. Right? So down here, if we've got, we want to find the entire base, well, we just made base over 2, right? It's half of the base. And our height is unknown. It's not the radius. The radius here will be this hypotenuse of the right triangle. And they gave us that the radius is 4. So each of these pink lines is 4. All right. The last thing that we need to know from it, if each of these angles is 45 degrees and the altitude cuts it in half, then this angle there will be half of 45 degrees, which will be 22.5 degrees. So if I redraw this right triangle, just so it's a little bit less cluttered, and we have a right angle. The leg down here is half of the base. Up here we have the height. Again, neither of those is known. But we do have that the hypotenuse here has a length of 4 centimeters. And the angle up top is 22.5 degrees. Using this right triangle and using our basic trig properties, our basic trig functions, we know if we want to find this base here, or we're finding the base over 2, and we use that to find the base, that's the opposite of 22.5. It's across from it, so that's opposite. And we know the hypotenuse, so that would be the 4. So we think which trig function uses opposite and hypotenuse. In this case, that would be sine. So sine of 22.5 degrees, and sine, you can think of that as so. It's sine of theta will be equal to the opposite over the hypotenuse. In this case, that would be base over 2 divided by 4. Right? That's the opposite divided by the hypotenuse. Now, using this equation that we just wrote, we can solve for the base by multiplying both sides by 4 to get rid of this 4. That gives us 4 times the sine of 22.5 degrees equals half of the base, right? Base over 2. Now, we don't want to solve half of the base, we want the entire base. So I would go from here and multiply both sides by 2, which would give 8 times the sine of 22.5 degrees equals our base. Right, now, from this first step, you could have just multiplied by 8 to get rid of the divide by 4 and the divide by 2 all in one go. I just broke it up because some people got a little confused when I did it the last time. But so now we have the base, and we know we want to find the perimeter, and the perimeter of an octagon will be, or the perimeter of a regular octagon will be equal to 8 times one side, right? Because it's all the sides added up, all the sides are the same. So for the perimeter, we're just going to take our base and we're going to multiply it by 8. In this case, that's 8 times 8 sine 22.5 degrees. Note that I didn't round until I'm getting to the part where I need to give the answer. So in this case, I'll do 8 times 8 sine, and make sure that you're in degree mode. We have 8 times 8 sine of 22.5 degrees. That gives me 24.4917. So again, I'm going to round beyond what I need. 3967. All right, so if we're rounding to the nearest hundredth, 1 will round down, so it would be 24.49. Our units were centimeters, so perimeter will stay in centimeters. Now, what is the area of the octagon? I did see some people use a formula apparently for a regular polygon inscribed inside of a circle. There is a formula that you can do 1/2 times the perimeter times the apothem, which basically is just finding the area of all of these triangles that way. I'm going to think of it directly how we would in class. So that's find the area of one triangle and then multiply that by the number of triangles. We need to find that height. Again, the 4 is not the height. So what we need to do to find the height, if you look up here, that's adjacent to the 22.5 degrees. So if we want adjacent over hypotenuse, that's cosine. Cosine of theta equals adjacent at the side that's touching it, that's not the hypotenuse, divided by the hypotenuse. In this case, that means cosine of 22.5 degrees is equal to the height over the hypotenuse, which is 4. So now if we want to find the height, you just multiply both sides by 4, giving us that the height is equal to 4 times cosine of 22.5 degrees. All right, so now we have the height. We already have the base from up here. So if you want to find the area of one triangle, well, the area of a triangle is equal to 1/2 times base times height, or you could say base times height over 2, which will give us 1/2 times, again, our base. I'm going to type it in exactly as it is up here, 8 times the sine of 22.5 degrees times our height, which is 4 times the cosine of 22.5 degrees, which gives us 1/2 times 8 is 4. 4 times 4 is 16. So the area of one triangle is 16 times sine of 22.5 degrees times cosine of 22.5 degrees. All right, we're not done yet because they don't want the area of the triangle, they want the area of the octagon. The area of the octagon is equal to 8 of those congruent triangles. So, right, area of the oct is equal to 8 times the area of the triangle. So in this case, that's equal to 8 times this value. I'm just going to copy it, paste it over. 8 times 16 times the sine of 22.5 degrees times the cosine of 22.5 degrees. Now I'm going to type that in exactly as it is there. So 8 times 16 times sine of 22.5 degrees, close parentheses, times cosine of 22.5 degrees. And make sure you're in degree mode. That gives me 45.254834. We round that to the nearest hundredth. That would give us 45.25. In this case, it would be centimeters squared. Last step we'd find is find the area that is inside the circle but outside of the octagon. So again, that's an area that I started by coloring those in purple. Now, to find an area that's outside of one shape, inside of the other, you just find the area of the outer shape and then subtract the inner shape. So in this case, we need to find the area of the circle and then subtract the area of the octagon. All right, so in this case, the circle is going to have a radius of 4. So if we do the area of the circle is pi r squared, that's pi times 4 squared. And then we already have our area of the octagon. That was our answer to the last question. So make sure you store that value in here. So I'm going to push our store button, store it as A. You can also retype it all in. But again, don't round until the end. Or if you're going to use a value, use this value here. Right? So it's not rounded until the very end. And 4 squared is 16. So that gives us 16 pi minus the area of the octagon. So I'll type that in. 16 times pi minus the area of the octagon, so I could do minus 45.254834, and I could use the stored value I had there, and that gives me approximately 5.01064847. So again, don't use the rounded value of the octagon, don't use a rounded value of pi or 16 pi, don't round until the very end. So we've got this thing way beyond what we need to the nearest hundredth, 0 round down, so that just stays as 5.01, and it's an area. Our units were centimeters, so it's going to be centimeters squared. All right, so that's how you find these 3 answers here. Make sure you show all of your work. You do need to use 2 different trig functions. Now, some people use this angle to find the height, so they could still use sine, that's fine. Just make sure that you use a different trig function to find the height and the base. Some people also use the Pythagorean theorem, so once you have one of them, you could plug that in and get the other. The one issue I'd have with that is if you mess up one of them, then that guarantees you also mess up the other one. Now, since you're using both base and height, will probably that would probably end up messing up your answer anyway. But that is another option if you'd like to do that. Just make sure again you're not using the rounded values when you plug in the Pythagorean theorem you want it to be, or at least round it far beyond what you need. All right, so the next one is number 7 here. In this case, we have a circle inscribed in a regular dodecagon. I believe I have to go get ready for class. So I'll probably record this one later if you notice the lighting change. But this one is pretty similar. I guess in this case, the radius will be the apothegm instead of the hypotenuse of the right triangles that you make. So that in some ways simplifies it, some ways makes it a little more difficult. So we'll go over that next. Now we're at question 7. It says a circle is inscribed in a regular dodecagon. So the circle is inside of the polygon this time. A dodecagon has 12 sides as shown. The circumference of the circle is 24 pi inches. So we know that the formula for the circumference is pi times diameter, or you could also write it as 2 times pi times the radius, right? 2 times the radius is the diameter. So in this case, that means that 24 times pi, if we divide both sides by pi, we get that 24 equals 2 times the radius. So our radius will be 12. Now we can draw 12 triangles here by connecting the vertices to the vertices that are across from them. Like so, and you could say I didn't do it perfectly there. Since it is a regular dodecagon, all of these sides are the same, all of the angles should be the same. Now if we want to find the angles up here, we'd go 360 degrees for the whole circle, divided by 12 because there are 12 congruent slices, and that will give us 30 degrees. So each of these will be 30 degrees up top. All right, so those lines that I drew that divide up the dodecagon into slices, you can see are not actually radii though. Right, so the radius is a little bit shorter than these lines. You can see the radius would end there, it's extending beyond it. So if we actually are to draw the radii, they would be the heights of these little triangles. And in this case, we'd call that the apothem. If you remember, that was in the vocab section. The radius that we solved for, that 12, would apply to the height. We are asked to find the perimeter of the dodecagon and the area of the dodecagon. To find the perimeter, we just need to find the base and then multiply it by the number of sides, because the perimeter is just going to be all the sides added up. They're all equivalent, and there are 12 of them. So to find that, we can make this triangle using 12 as our height, right? 12 is the apothem. We know that it's an isosceles triangle because it's a regular polygon. And we said this was 30. So when we drop that altitude down, that's going to split it in half into 15 and 15. Again, because it's isosceles. Essentially what we end up with is a right triangle where one of the legs is 12, the other one is half of the base. Again, the base is what we're solving for. So we could say this is half of that base, if the whole thing was B. And we don't know the hypotenuse, but we do know it's a right angle there. We do know that the angle up top is 15 degrees. It's half of that 30. So if we want to think about which of our trig functions would relate this base over 2 to the 12 that we know, that's opposite the 15 and adjacent to the 15. So the one that includes opposite and adjacent is tangent. Tangent of theta is equal to opposite over adjacent. So in this case, that would be tangent of 15 degrees is equal to half of the base, so base over 2, divided by 12, the adjacent. To get the base alone, we could multiply both sides by 12 first. That will give us that half of the base, so base over 2, is equal to 12 times tangent of 15 degrees. And now we can multiply both sides by 2. Again, you could do that in one step and just multiply by 24 from the get-go to get rid of the divide by 12 and the divide by 2. But just to avoid any confusion, doing it as two separate steps, and that gives us the base is equal to 24 times the tangent of 15 degrees. All right, so now we know that what the base is, and the perimeter, as we said, is just the base times the number of bases, which in this case it's a 12-sided shape, so there are 12 bases. So we just do 12 times b, which gives us 12 times 24 times the tangent of 15 degrees. I can type that into my calculator. We get 12 times 24, which would be 288, times the tangent of 15 degrees. Make sure you're in degree mode. And that gives me 77.169366742. They want us to round to the nearest hundredth where necessary. So this is a final answer, so I can round it. 77.169 will round to 77.17. Our units were inches. So it would be inches. You don't have to square it, and you shouldn't square it because it's a perimeter. To find the area, we need to find the area of one of the triangles. So area of one triangle is equal to the base times the height over 2, or you do 1/2 base height. And then, again, the area of the dodecagon, area of dode, is equal to 12 times the area of the triangle, right? Because each of those triangles is congruent, and there are 12 of them total. So our base we have up here is 24 times the tangent of 15 degrees. Our height is given, right? The height is the apothem right there, that times 12. And then if we divide by 2, it gives us the area of the triangle, which is 24 divided by 2 is 12. So 12 times 12 is 144 times the tangent of 15 degrees. Right, so now we plug that into our area of the dodecagon. That is just 12 times the area of the triangle. So now it will be 12 times 144 tangent of 15 degrees. That's essentially 12 cubed times the tangent of 15 degrees. 12 cubed is 1728. Tan 15. So if you wanted to leave it in terms of the tangent, sometimes people will ask for that. And this is technically the more exact answer. But generally, people will write this as a rounded value. So we could type this into the calculator, make sure you're in degree mode, and it gives us 463. They write it gives us 463.016245. If we round that to the nearest hundredth, that would be 463.02, and this time it will be inches squared because it's an area. Right, so either of those answers is technically acceptable. Most of y'all would probably write it like this, rounded to the nearest hundredth. Based on your answers above, if the entire figure was scaled up such that the circumference of the circle was tripled to 72 pi inches, it started as 24 pi inches, so our scale factor is 3. It's 3 times bigger. What would be the new perimeter and area of the scaled up dodecagon? For a perimeter, what you do is you just multiply it by the scale factor, right? Each side gets that much longer, so when you add them up, they're all that much longer. So essentially, we could just take this 77.16936.742, and we're going to triple it. So I can just type that to my calculator, times 3 gives me 231.5081.023. Okay, so this is the new perimeter. You can say this is like the old, and now we have the perimeter new. Is equal to 3 times the old perimeter. It gives us 231.5081.023. So that would be 231.51 inches. Okay, so this is our scaled up perimeter. For area, you actually have to multiply by k squared. The reason for that is that you're basically increasing it in 2 different dimensions. So you could think of like a triangle, the base and the height are both being scaled up by a factor of 3. So you have to multiply by 3 for the height and for the base. So in this case, 3 squared, that would be 9. So our new area is equal to the old area times 3 squared. So it'd be 9 times the old area. Now, our old area, we have it right here. Now, our old area is 1728 times the tangent of 15 degrees. So we just have to multiply that by 9. 9 times 1728 tangent of 15 degrees in degree mode. And that gives me 4,167.145841. And then you could round that to the nearest hundredth. 58 will round up. So it's 4,167.15. Because it's an area, the units will be squared, so it's inches squared. So that would be how you do that. Again, for this one, it's 3 times the perimeter to get this, and it's 9 times the area to get this. You could also just use the already rounded answers. I generally gave credit, but if you want it to be very exact, then I would use the unrounded answer. You shouldn't round until you're very, very end. Just make sure that you're keeping track of your units and that you are breaking down your problems step by step. All right, well, hopefully this was helpful, and if you have any questions or lingering concerns, or if you feel like there was a better way to do one of the questions than the way I did it here, feel free to comment below.